series of online series of seminars. Delighted today to welcome Professor Lars Kunze, who's currently Professor of Safety for Robotics and Autonomous Systems and co-director of the Bristol Robotics Lab at the University of the West of England. He's also a visiting fellow at the Department of Engineering Science at the University of Oxford. Technical lead at the Responsible Technology Institute. He's also editor-in-chief of the German Journal of Artificial Intelligence and editor of the Journal of Responsible Technology. His interests are in robotics and artificial intelligence, very core to what we're actually doing here today, and the focus is on combination of knowledge representation, reasoning, machine learning, and robot perception, and with a real interest in complex real-world environments, which is an interest we all share. Okay, take it away, Lars. And thanks for being our inaugural speaker.
Thank you very much, John. Thanks. Let me share my screen. Hopefully that works. I'll get rid of this. Let me just move this across. Okay. Hopefully you can see that. Yeah, my screen now. Excellent. Okay. Hello, everyone. My name is Lars Kunze, and I'm really excited to be here today in this kind of seminar on safety and secure robots from the Crane Network. In today's talk, I want to talk about how we can make robots and robotics explainable, and thereby also safe and trustworthy. And of course, whenever I mention safe, it also includes security as well. So I think also I won't focus much on security aspect today. So I think that's always something I'm quite interested in as well. So let me get started with slides. So we have seen a huge advancement in robot technology over the past decades. And this is both in hardware and software. And so today we are able to deploy these robot systems on our roads, in our factories, care homes, hospitals. And this is possible due to this advancement in, as I said, software and hardware. So we have new sensors, new actuators, but also deep learning and foundation models have really changed the way we can interact with these systems. However, the question is how we can really unlock all the societal benefits for these robotic systems. And I think a key challenge here is that these robots are developed against this ethical, legal, and social background, right? So we need to consider safety, accountability, and trust at the forefront. So although the technical challenges are really difficult to overcome, but these things are really important to tackle as well. And in today's presentation, I want to go a little bit or give you an overview of what we have done, in particular my background in robotics kind of over the last years. Kind of I've worked on different platforms, kind of from small mobile platforms, service robots in everyday environments to autonomous driving. And that's something I want to talk a little bit about today. And I will mostly focus on these kind of platforms that you see here. So on one side, autonomous driving, because I think it's really important as it's kind of really safety critical systems when we deploy them and put them in our towns and cities. But also, of course, service robots, which can maybe be deployed in hospitals, care homes, as I mentioned, office environments, or at home. And so that's why I want to start with these. So let me start with a project on long-term autonomy. So this was a European project called Strands, and one of the aims here really was kind of to put robots in our environments for long durations of time. And the Strands project was very successful in doing that. So we were able to achieve a year of autonomy across multiple platforms and environments. And this is kind of without any expert intervention. So this was a major achievement in the robotics community. And these robots were able to carry out many tasks, over 20,000 tasks. And if you have deployed a robot system, you know that this is very hard, right? So these are open-ended environments. These environments are highly dynamic, and there are many safety critical issues as well that you need to consider. So on one day, kind of when we were kind of meeting with the entire project team and we were just kind of developing new features for the robot systems, we were all sitting together in a lecture room, had our heads down and just coding, right? And what happened, we heard a really loud bang, and then another bang and another bang. And what has happened is that one of these robots that you see here in the video has kind of went down the staircase. And of course, yeah, no matter how much you prepare, and if you deploy these robots in everyday environments, so accidents will happen, right? And it took us quite some time to understand what has happened and why it has happened. But imagine kind of if you had an explainable system, so imagine what the robot could have explained either before the accident or then after the accident maybe has happened. So what went wrong and why, right? And it took us a while to figure out what the kind of navigation system caused an issue here, what the issues are. But I think so. This is one of the key motivations why explainability is quite important in hindsight, so post hoc explanation, but also foresight to prevent such accidents. Okay, so this brings me basically to the outline of my presentation for today. In the first part, I want to talk about kind of how can we build up a good understanding. So how do we go from pixels or sensors to explanations? And then once we have built up this causal understanding of the world, I want to explain how we can use that information to make better choices within our environments. And once we can make these better choices, I want to explain how these allow us to trust in these systems. And finally, I would just want to wrap up everything and want to go from understanding to impact. Okay, so let's start with the first part where we turn observations into a causal understanding. And I want to start with one project we did in the autonomous driving space. So this project is called SAX, Sense, Assess, Explain, and it's basically going from sensor measurements to explanations, right? And as you see, so here there's a platform we have been using in various deployments. So we deployed this platform across the UK. So here you see a video of our trials in Scotland. But we also managed to run it in New Forest, Oxford Ring Road, and the city centre of London. And during these deployments, we are collecting quite a lot of data. So you see that we are collecting over a terabyte of data per hour. So which is a huge data set, of course, kind of to go through and to extract the relevant information for all these different situations. So we have cameras, I think over 15 cameras. You see the spinning LiDAR Velodyne sensor at the top. So this creates point clouds, and we have multiple LiDAR sensors as well as radar. So all of this information need to be taken into account, or some of it, and then we want to generate explanations from that. In particular, we also worked on a kind of subset, a data subset. So here you see in a second kind of a recording from our deployment in London. And what we focused on here is commentary driving. So commentary driving, if you don't know, it's an advanced driver technique that drivers use, and while driving, they basically verbalize or speak out what they see, how they interpret the scene, how they evaluate the situation, and what they're planning to do, and so on. So this is just to give you an example here of how this sounds and looks like when somebody is using this technique. So it's used, for example, in advanced driver training courses, but also by the police force, because it really raises the attention of the driver. So I want to play you the clip, and hopefully you can hear it. Please shout if you cannot.
Now I'm on the bend here, so I'm going to move out a little bit early, but not commit myself for the overtakes. I've got the bus and the bollards, and there's a lot going on there. And I've got another bus on the other side and the truck coming. It's just easy to hold back, let the cyclist take his position. The bus is moving out now. Come car's sticking out far more than it should do, so I'm just going to move out a little bit. And now the bus is indicating, so he's going around a blockage, I'm assuming he's going around the cyclist. So the cyclists are moving different speeds. We've got a car coming up. Just going to hold back to see if he's going to go for the overtake. He is. Now the bus is pulling in. Now I can overtake both of them. Go on. Just make it safer for everyone. Now I've got space to come around.
So this was really to give you an idea how this explanations in commentary driving look like. And so that's kind of our motivation to generate such explanations for a driver assistance system, for example, for autonomous driving. I already motivated that explanations are quite important if we think about accidents, so kind of post hoc explanations. And we want to have those for transparency, accountability. But explanations also will allow us or make the systems more useful and trustworthy in general. And sometimes we need explanations because of compliance reasons, or if you need to comply with certain regulation and standards. These explanations might be generated for different stakeholders. So in this case, it was kind of the end user here, maybe a passenger or the driver in the vehicle, right? But potentially we want to generate those explanations as well for developers or regulators. And there can be different types of explanations. We can have causal explanations, contrastive explanations, counterfactual explanations. And so it's really important that we tailor these types of explanations also to different stakeholders and the content what we generate. And aside from that, we also, of course, need to think about other aspects like the succinctness of explanations, because we can explain a lot, right? But we also need to be precise what we want to explain, what we need to explain. And all of this, of course, needs to be comprehensible and also faithful to the system state, right? Currently, we also see the rise of language models and so on. So we need to make sure that whatever we generate and explain also fits with the actual state of the system. So here is a kind of an envisioned framework how we see that in the context of autonomous driving or any robot system, really. So at the bottom here, you have the default stack, kind of the AV stack, for example. So going from sensors to perception and localization to behavior and motion planning. And then based on this, we will generate control commands and actuation commands. And we mirror this framework also on the explainer side. So we believe that an explanation system and explainer should have access to all this information in terms of perception, localization, planning, and control. And then this explainer system can interact with, for example, accident investigators or passengers, right? And so there could be different user interfaces, how they might query the system, and then the system is able to provide some answers to that. So I wanted to explain how we go from pixels to explanations, right? So here is a typical driving scene in Oxford. And if we want to go from an image like this to a high-level explanation, which says the current lane only allows us to do a right turn, and we need to change to the left because our goal is straight ahead. So we need to combine basically our perception systems here, but also our action planner. And we have worked on this kind of, first of all, using deep learning technologies. So semantic segmentation algorithms can be trained using kind of different machine learning methods, and then we can extract relevant information from these images pixel-wise, right? But that doesn't really get us already to the high-level natural language explanation. So what we did instead is, based on some of these pixel-level semantics, we generated scene graphs. So scene graphs are basically graph-based representations of the scene, and a scene here can be composed of a road or multiple roads, and one road can have multiple lanes, also bicycle lanes. And then this the road and the lanes are grounded in pixel data, basically. So they have some grounding in sensor data, the different types of road markings, the arrows, for example, and the curbs. So all of this is kind of grounded, and this works also for other sensing modalities. So this gives us an easier way then to go from this graph-based representation to natural language explanation. And here you see that we can not only do this for the road infrastructure, right? So the static elements, but also for the moving parts. So we have, of course, lots of road users, and we are able to generate these scene graphs for the different road users. So we always have the ego car centric in our graph, and then we model the relationship to the other road users on the other lanes and etc. In relationship to the ego vehicle. So this also represents then kind of the sequence of graphs represents the kind of dynamic development of the scene. And putting this together, so we were able to come up with an automated commentary driving approach. So we had input from camera data, we were able to generate these graphs, scene graphs, and then using a template-based sentence generation method, we were able to generate sentences like this. So the vehicle stops because the traffic light turns red. And this is quite useful to have this as a rule-based approach. So you can think of this similar to a decision tree, which we can interpret, and because this gives us the ability also then to look up counterfactual explanations, right? So we can go along this decision tree and think about a different context, for example, when the traffic light is not red but green. So we can evaluate what the car would have done in a different situation. As I mentioned also earlier, so these explanations also need to be comprehensible, right? So we really also need to evaluate how useful they are to participants. So we have run some experiments in this user study with about 40 participants. And in our setup, we used Carla as a driving simulator. The participants were a passenger, basically in an AV car. And so we had kind of eye tracking data, but also then kind of had a questionnaire for the participants afterwards. So they were exposed to different explanations while driving through different routes. And so what we evaluated here is basically the perceived safety or the anxiety of the passengers within these situations, given the different types of explanations. So what we kind of looked at here in terms of the different types of explanations were kind of very vague explanations. So instead of referring to a pedestrian and cyclist, we would just refer to a road user. So this is quite useful because then the latest step of inference can be done by the passenger or driver. But it also helps with our system in the sense that our perception systems can of course make errors, right? And if we refer to a pedestrian, but it's actually a cyclist or the other way around, so this will only create confusion. So this vague explanations by referring to just road users is quite helpful in this context, and it was still perceived very safe. And the other conditions, we simulated some perception errors. And here it is also clearly visible that kind of the lower error rate is actually better. So if you have a perception system that makes less errors, then of course it's also good to refer directly to pedestrians and cyclists and so on. So I think the study showed basically kind of quite what we expected in the first place. And so these scene graphs are really useful to go from kind of different events to causal understanding, from events to causes, because they also explain in what situations we are. So we looked at this sequence of causal graphs and generated using graph neural networks, we generated these graph embeddings. And Here you see some kind of clustering of these embeddings in relation to the vehicle action, and you see also how nicely these clusters form here in relation to the vehicle action, so we can really make use of these embeddings in other downstream tasks and have a better understanding of the situation. So here was one task where we looked at the prediction of the next vehicle action based on our sequence of graphs. And you see as kind of a general outcome, so that we were able to predict the motion or kind of action of the vehicle quite well here in this case. Another use case is really to find similar scenarios in our database. And so, for example, if we are interested in scenarios where the vehicle stops at a crossing or turns left at a junction, we can then use these generated scene graphs to find and embeddings to find other similar scenarios in the dataset. So this is quite a useful application because it helps us to search quite complex data structures using these graph-based embeddings based on these causal models. And once we have found these kind of similar situations, we can then also use them to generate new scenes or new contexts. So for example, if we're interested in safety critical scenarios, we were able to generate these scene graphs from real world data. And then we modified these graphs using temporal link prediction. And this allowed us to generate new scenes in color. So we modified them in a way that we generate safety critical scenarios so that we can test and validate actually the AV models towards more these safety features and safety aspects. One last part on explainability. Of course, we have also tried vision language models or multimodal language models for explainability generation. And here you see our work from a couple of years ago where we were able to predict basically the action of the vehicle. So similar to what we did on the graph-based side, but now directly using an LLM. So predicting the action, also coming up with a justification. So very similar to what we've done with the template-based sentence generation. And then we were also able to predict control signals of the vehicle based on the input data. So obviously, this has a huge potential, I think, in terms of evaluating robotic data, not only in this domain, but also other domains. But of course, it comes also with some limitations, in particular, if we think about transparency and traceability. So I think it's a really exciting area, but I think there's more work needed here so that we can make sure that whatever is generated in these contexts, so that this is also faithful to the system state. So this is, I think, a really exciting area I'd like to continue to work on. So just want to briefly summarize kind of what we've seen so far in terms of how we go from pixels to these representations, explanations. In the lab, what we often do is we start with kind of a platform, so either a mobile service robot or vehicle that we have now seen here. And around that, we design these kind of different algorithms for scene understanding. So I talked about the scene graph representation to really understand the semantics of the scene and to build up these graph structures. We then also use causal models to either discover new causal relationship over time between agents or then to reason about these things. And based on this, combining these two elements, we were able to generate also contextualized explanations. And in our work, often this is kind of, or usually I would say always grounded in responsible innovation, where we also work in projects with stakeholders from the outset so that we really understand their points and kind of the critical points around safety, but also trust and accountability. Okay, so this was a the first part, so how we go from pixels to explanations and how we build up this causal understanding. And in the second part, I want to talk more about how we can use that causal understanding, causal reasoning to make better decisions. And to do this, I switch domains now. So really the question is how we should use or how causal explanations can shape decision making. So if we look into the future and have to act, for example, by picking up an object, so how can we use these models to make better predictions and inform our decisions? And so here's an example of a robot doing everyday manipulation tasks. So that's a very simple task here that we have simulated and also implemented in real world scenarios. So the task is just to pick up objects and put them here in the kind of tower configuration. So it's a block stacking task, just using these 3 blocks. And the main question here is that we're looking at is how do we place the last block depending on the first 2 blocks, right? Depending how good the second block in the middle is placed. So we need to think about, of course, kind of where we put the last one. And this requires us to reason about different things. So we need to think about is the tower stable, right, when we put the next block or the last block down, and what would be the best action or best action parameterization here. And of course, the challenge is that we only have partial observable knowledge from perception. So we have our perception input data the robot is using, but also our control actions are stochastic. So the motions are not always executed perfectly. So in the real world, so this of course is challenging. And this is something we have actually also modeled in our reasoning framework. So in our approach, we adopt kind of a causal Bayesian network approach here, which describes the decision-making process of the robot. So we have our actions, which we take in certain situations. So our actions are modeled here with A1, A2, and our observations in certain states. So states are described with S0, S1, and so on. And then observations are Z0, Z1, and so on. And so this is a model that we can roll forward for the decision making of the robot. And using this model helps us really to model the causal relationship between our kind of perception and actions. And we don't just have a correlation, right? So we have a causal model here. And so our causal model semantics also allows us to do causal treatment. So we can do reasoning within this model. And we have uncertainty directly encoded here as random variables. So the uncertainty in terms of the action execution, but also the uncertainty from the perception system. And this is combined with a physics-based simulation. So we perceive a state. This is something then we set up in a simulator internally of the robot before we act on it. And then the robot is running multiple simulations and is evaluating different configurations here of these parameterizations. And so we are able to predict the outcome of our actions before actually committing to them. And this is quite powerful in terms of the approach. So here you see the overall architecture, just to give you an idea. So on the left-hand side, we have our environment and the robot system, similar as before. So we have perception, reasoning, control paradigm, and then the inference kind of involves our decision model, our causal model, and the physics simulator as well. I only want to briefly go into the results here. So we are quite good in predicting the stability here of the tower, and we also can perform our actions relatively well compared to a relatively simple baseline, especially when we don't have or when we rely on sensor information, our approach works actually quite well. So not under the ideal assumption that we have full access to the simulator data, but if we have noise in terms of actuation and perception. So our approach works still very strong. And so I think it's really helpful kind of to have this reasoning, because then this allows us to take this into account for our decision-making approaches. Okay, so I think this was the second part of the presentation. So where we went from basically our causal models to our action selection. And in the last part, I want to briefly talk about how we go from better actions to trust, and why explainable decisions enable trustworthy autonomy, in my view. Okay, trust, of course, is influenced by many things. So here is a figure that is by Alan Winfield and Marina Dorotka, and it's kind of part of the Robotics project. And so trust is, of course, influenced by ethics, standards, and regulation. And so a technology, I think, can be trusted kind of if it brings benefits, right? Benefits to end users, but also if it's really safe and well regulated. So safe, physically safe, but also psychologically safe. I think these two things are quite important. But also, I think we trust the technology when we can investigate it, when it's robust to investigation, right? So when an accident happened, as I talked earlier about, so I think it becomes really important that we can understand the reason why this happened. And so yeah, here's just a reminder of that. So as I mentioned, so accidents can happen in everyday situations as well. So not only on the road and with service robots. And so the idea of the Robotics project was to equip every robot with a black box, it's called ethical black box, that would aggregate and analyze continuous robot data. And so the idea is that every robot should have one, similar to a flight data recorder. So whenever something goes wrong, you're able to investigate that. And that's, of course, really powerful when you think about kind of safety or security breaches. So you are able to investigate what went wrong and why. And yeah, so in this sense, I think the trust emerges not only when we see a system that performs well, but also if we can understand the reasons why these actions have been taken. And so these reasons would be captured also in these ethical black box systems. So I want to go back. So in the previous part, we looked into the future kind of for decision making, but now imagine that we're also logging all this information in our ethical black box, and then we want to interrogate this black box system in some ways. And the main idea here is really to use a dialogue system to interrogate the robot's black box. There can be, of course, very different mechanisms, but this project looked a little bit into a human-machine dialogue. So this was kind of slightly before ChatGPT when we started with this work. So this should sound very familiar now. So we raise a question to the robotic system, and then we receive an answer. And this is, of course, kind of all structured in a conversational dialogue. So we have our conversational context, and then our answers are generated back to us. Here, of course, we also have the addition that we have an embodied system, so an embodied question answering. And so we link these questions to the robot knowledge base. And given we have everything represented using these scene graphs and use a more maybe traditional or kind of semantic web-based representations, we are able to pull out this information from the robot's knowledge base and also from the episodic memories, and then are able to generate these answers based on our observations. This is also what we established for our robot that I presented earlier. So we are able to raise certain questions and to interrogate the robot really about why certain decisions have been taken, and what happened. So the robot would be able to explain why it took the decisions and how the outcome came about. Okay, so this already brings me to the end of this part. So I think really explainable decisions require these causal reasoning capabilities. Hopefully, I could motivate this, and so that we can have systems which are trustworthy in principle because they rely on these causal reasoning algorithms and frameworks, but then also trusted in practice because we see how they can be interrogated and be useful. Okay, to wrap things up, so in my presentation, I talked about kind of how we go from pixels to explanations and causal understanding, and then from this causal understanding to making better choices in our actions. And then once we have these better choices in our actions and better decision making, so how this would also generate trust, in addition to the systems we need in terms of monitoring and logging this information and being able to interrogate those things. So hopefully I could motivate that causal abstractions enables the safer decision making. But I think what's missing, so I've highlighted a few parts that we have done in our work, but I think what's missing for me is kind of a more comprehensive cognitive layer for safe and trustworthy autonomous systems at scale. So, and I think that's really where I see a value in this network, because I think this is really where we can work together on issues and problems in the context of safety and security, and how we can bake these really into the layers of these systems. We also have an ongoing project called PACER, so where we're looking more into proactive explanations, making decision making for this. And overall, I really hope I could motivate why causal explainability can address these issues around safety, accountability, and trust. So it would be really fantastic to create these shared building blocks together as a community through the network. And before I stop, I just want to plug two things because I think it's quite good for the network to know about these things. So we have an ongoing PhD PhD student called Patrick Robinson, who is working on safety and security assurance. He's really looking into kind of the cross-layer assumptions in robotic systems. So similar to the bigger architectures I've shown earlier. So his interest is really about the assumptions we are making when developing and building these systems, how things are communicated, encoded, and so on. And he's doing kind of work with kind of empirical systems research with focus groups, and so it's really engaging with robot practitioners. So I think there is a great way to interact with him in this regard, but also he's developing and designing a robotics test bench framework called Rotifer. And so this is really focusing on ROS2. So if you are interested in particular also this robotics test bench, so please scan this QR code and join the mailing list. So I think that is a great opportunity to work with him and the team on this. And very briefly, we have an open PhD studentship on safety assurance for robots for swarm robotics. I haven't really talked about multi-robot systems today. So the deadline for this is next week. So please share this as widely as you can, so with your students and colleagues. And please contact Sondes Mizawi. She's based in UE in computer science, but this is joint work with the BRL, and I will be involved as a co-supervisor here. So this is another great opportunity to work in that space. So I'll stop here. Thank you very much. And here you see a picture of all the people who have done all the brilliant work. Thank you so much.
Thank you very much indeed, Lars. That was a great talk. Great talk. I have some questions, but I think other people should get priorities. So does anybody have any questions? Just put your hands up. Yeah, that's right. That's a good response. Okay, Ali, sorry.
Hi. Hi, good afternoon, everyone. Thanks, Lars, for the great presentation. Quite like the presentation, and it's in my area of interest. The question here I've just got, you did mention about security, and this is what I'm interested in. Uh, have you guys within your team consider the crowd sensing environments? Because I saw even within the potential PhD, you want to talk about swarming concept. And this is where getting a bit more challenging. In the previous scenarios that you've showed is more about one, let's say, autonomous car driving or one robot. When getting swarm or crowd sensed kind of environment, this is where getting more challenge, especially in terms of the security. I don't know if this is something that has been investigated. And the other question I've got here, which is more about the trustworthiness, which you mentioned. I do understand that you mention and you touch base mainly about explainability point of view. And also, I would love to also have a bit of insight because not any trusted things is trustworthy by nature. So, how do you guys measure that kind of trustworthiness, if let's say, of the scenario of overtaking as you describe it? Thank you so much.
Yeah, great questions. So yeah, let me start with the security angle. So I think that's a bit kind of related to the work Patrick is kind of starting to look into. So I haven't really worked on the kind of security angle so far, but I think he's quite interested in the kind of connectedness of different systems, right? So, I mean, you can already think of one robot, right, as a connected set of sensors, and you want to maybe swap in one sensor, swap out one actuator, and so on. And so that, of course, scales when you think about multiple robots, then communication with the infrastructure, and how you keep everything secure even if things change over time, right? So I think that's a really interesting question, kind of when you think about the dynamics, long-term dynamics and deployment of these systems. And I think, yeah, he looks into this kind of relationship and kind of when you change something in one part, how does this impact the rest? And I have another PhD student who looks into similar aspects from the safety perspective a bit more. So I think what we need really is kind of consider security from the outset. I'm not sure how to do it. Often, kind of in my experience, is kind of security is thought about kind of, or is often an afterthought. And when we do research in robotics, it's often not considered, right? So it's something which we kind of postpone and say we do it when we deploy this, or maybe industry deals with it. But I think we need to maybe think a bit more about this from the outset. So I think this is exactly what kind of Patrick's work will be about. Kind of the other question on trustworthiness. So I think for me, the kind of trustworthiness is often when you have systems that are more by design trustworthy. And this is, I think, when we have methods that we can engineer and interpret, right? So, and it's really hard, I think, for me to see kind of how we can do this at the moment, at least, with some of the large language models and vision language action models and so on, because it's really hard for us to understand what is happening inside here. So I think, so trustworthy by design is something which I think is for me quite important, so that we are able to inspect, trace, and interpret these things. And I fully agree with you, as you said, so it doesn't often correlate with trusted system, right? People trust systems like ChatGPT, or they simply trust this because they get good answers from them. And this is not kind of a causal relationship in that sense, right? So that's something we need to investigate, I guess, differently. Also, trust builds up over time and kind of is lost within seconds, right? So it depends really on how the system often performs. Another student of mine is looking into also psychological safety and how people feel kind of within these systems or using these systems. So perceived safety and this kind of dimension is something we are exploring as well. Yeah.
Thank you so much.
Hopefully that gives answers this a bit. Yeah.
Yeah, definitely. Thank you so much.
Frank? Frank van Laarhoven. A question?
Frank,
Oh,
you are muted.
Yes, you are muted.
Go ahead, Frank. You're muted.
Oh, sorry. Sorry, can you hear me?
Yeah.
Mhm.
Right. Okay. Now, yes, thank you very much for your, for your presentation and everything. I really like it. Part of my research is robotics as well, robotic safety. My question was basically based on the the black box issue, and that's something I'm trying to obviously solve with part of my research. The question here is basically like, how do we, have this explainable scenario where, you basically get a robot to gather all this information in a black box and then explain it after, rather than us having a long-term, direction where, we can have basically an architecture that is pre-built, for transparency, as opposed to, the ad hoc scenario that we have now.
Yeah, so I think that was part of the kind of Robotips project when they kind of thought about the kind of ethical black box to some extent. So the main motivation was more to look into accident investigation. So it's kind of a post hoc analysis, so similar to a flight data recorder. Of course, I think it's a big question what kind of data we should record and with what granularity, right? So as you have seen, kind of with the autonomous vehicle, so we are recording over a terabyte of data an hour, so we cannot keep all of that, right? And for how long should we keep it? And who has access to this, right? If something goes wrong, is it the user? Is it the manufacturer? Is it the insurance company? So I think there are really interesting questions around all of that. And so it's a question of kind of based on the application and task, I guess, kind of what is the relevant information we want to keep. So that's how we ensure maybe the robot system. And then, of course, what explanations are quite useful. So when we talk to insurance companies, often they quite like video data because that's something which we as humans also quite good at in interpreting, right? But then this also raises this kind of privacy maybe issues kind of when we record that data. So yeah, I think it's heavily depending on the application use cases. I think what we want to record, what explanations we need to design for these domains. But I think there is something like an underlying architecture below that. So I think kind of your question went in this direction so that we need to provide certain types of explanations, and hopefully then this framework is able to do this. And also what we are trying to do now is also to proactively provide explanations more in the future, kind of future looking. So this is kind of the work I was presenting in relation to the reasoning of the robot, right? When we roll out potential actions, so that we can explain things before things go wrong. So I think that's also quite an important aspect. So not only the post hoc, but also the more anticipating work.
Right. Because sorry to interject there. So last bit is basically just to add to what you're saying. My concern has always been, why, do at a post hoc scenario as opposed to, because obviously, we all know that information can be tempered, right? Black box, what I mean? So that's why in the future, we're actually trying to move away from the black box. Do you know what I mean? And especially with robotics, do you know what I mean? We do not know exactly what companies do with these black boxes that they put in their robots, and where they basically are positioned. So the question here is, okay, so who gets access to these so-called data? and basically, how can we are talking about trust and safety here. How can we basically trust it? And then that's basically the question that, I'm actually answers I'm looking for, basically. Yeah.
I think part of this, maybe just briefly, of the idea of the black box is that you kind of incorporate this into your system independently of the manufacturer or the kind of robotic integrator. So while you're logging data, it's not really part of your system. So, and also you are able maybe to then say that this data is not tampered or is quite secure because you're only feeding into this data. So then, of course, you can only or mostly use it for kind of post hoc explanation. But in a sense, if a company develops these devices and is independent of the manufacturer, so that could also, I think, increase trust, because you know that this system that you run at home or in your workplace is equipped with this data recorder, right? And if something goes wrong, an independent party can come and investigate what has happened. So it's not only with the manufacturer. So I think this is kind of an important, maybe part of the idea of this black box system. Yeah.
So lastly, if I may, so how do we align that with compliances with the government's regulations and stuff like that? Is there going to be any centralized, system where everybody then have to then go and get their safety net tested or compliance with? That, that becomes centralized to everyone, that it is like an ISO, for instance?
Yeah, I think so. I mean, for example, if you're looking at autonomous driving, right? So you have, or driving, even kind of driving in general. So new cars now need to be fitted with event data recorders. So they have kind of a capability of record certain events before an accident. So they are only introspective, or kind of looking only at the data inside the vehicle. So it's not looking at the outside perception of the vehicle currently. But I think the regulation is moving in this direction. So at least in this field, in this area, whether this becomes relevant for all and other robotic systems in other domains. So that needs to be seen, I guess, once you have a more standardized platform, maybe that is, I think, conceivable that this will happen. And then that you also have certain validation tests, maybe, which are more standardized and so on. So I think that's something which would be quite desirable, so that we have independent assessment of these platforms. But I guess also looking at the diversity of robotic platforms currently, so that will be a challenge, I guess.
All right. Hi, John, you're mute again. I think we have only 5 minutes left, and then we have a couple more questions. John, would you like to have a quick look at the chat? There are some interesting questions there.
I'll just look at the chat. I know I've got a list of people who've... sorry, I'll just bring up the chat itself. Okay, so we actually bring up the chat here. We have a lot of questions here, actually. Okay, any of these particularly... Okay, so here's one which I think will also affect security for industry. When we consider transparency and explainability, how can we ensure the real-time performance for safety critical systems, autonomous systems? So the real-time aspects, which actually comes into some of your earlier points when you're doing simulations for essentially to work out what the consequences are. So there's all sorts of real-time, very, very low latency loops. So the question is, when we consider transparency and explainability, how can we ensure the real-time performance for safety critical autonomous systems?
Yeah,
that's from Mary.
Yeah, it's a good point, Mary. Thanks for the question. So I think in our case, well, the kind of real-time aspect with the kind of block stacking isn't so critical. So that's why we had kind of more time, of course, to simulate and think about kind of the best outcome. So I would assume technology, of course, simulation and so on, inference method will become faster over time, so that will become less of an issue. But of course, if you think about the kind of other example I gave with autonomous driving, right? So if you are on the road and driving with 30 miles an hour, so of course you don't really have the time, you cannot afford to think about this. So I think it's also a question how essential it is. Is it only an additional system, for example, in that context? I mean, transparency is something which is still maybe baked in because we have the underlying representations and we can inspect those later, kind of whether there's an accident or not. So we are able to harvest basically these representations. But of course, if we want to explain something in real time, so then it's also a good question, when do we explain it, and do we have all the information, what to explain, and at what point? Yeah, so I think there are quite interesting challenges in this explainability part as well in that.
Okay, can I encourage people to put any more questions in the chat, and we'll take these down and we will return to these in our meetup meeting at the all hands meeting as discussion items there, because there are a lot of different things. If I just final question, Lars, can I ask you something very specifically on the earlier parts of your presentation when you talked about conversational reporting, essentially, so people, the drivers actually saying what they're doing. It seems that there may be a difference between what people say and what actually causes them to act intuitively. So that what you're actually getting is a sort of prioritization of what they think they should be saying, or alternatively, what's actually going through their conscious mind, rather than what's actually driving their driving in a sense. And is there a possibility there of actually using that information as a way, which is an expression of priorities, their conscious priorities, to explore things which are consistent with that, but dangerous, and using those as a sort of like an adversarial, to inform an adversarial scenario generation?
Yeah. No, I think, well, our research on explainability or automated commentary driving was driven by the experience we got from the driving instructor, right? So we had this kind of exposure to the driving instructor, and so it was really interesting for us to see what he picks out and what he's not commenting on, right? Because you cannot comment on everything. So, and in one situation he might mention the bus, in the other situation not, right? So why is that? So I think there's a really interesting piece here, kind of to understand that kind of in what context this becomes really important, and you don't want to miss it. And sometimes it's just maybe trivial, because in language you can only, of course, verbalize one thing kind of at a time, but we have a full kind of model underneath, and we also need to select where we pay attention to, I guess, and then surface this information. Yeah, it's a really interesting question.
Okay. I think at that point we'll bring the talk. Thanks very much indeed. I thought it was a great talk, and I've been writing down analogues on security. And I thought some of the questions on swarming, incidentally, and auditing were really important, as in why are you actually auditing information? Is it to say whether you acted reasonably given what you knew, which is a different issue as to what happened in a swarm environment where you might have multiple perspectives on things. So if the question is who are the stakeholders in audit data generation, and what are the variety of purposes it serves? And I think that's not an easy question to ask. I think we can put these sort of things down. We can use them to frame some discussion brainstorms and things like this at our all hands meeting. I think it's been really great. If anybody has any other questions, please put them down here. But failing that, thank you very much, Lars. I thought it was an absolutely great talk. It's beautifully presented. Beautifully presented.
Cheers. Thank you very much. Yeah, thanks everyone for the questions as well. And yeah, hope to see you all soon, and looking forward how the network evolves and develops. Great.
Yeah. Yeah.